Nice. Continuous probability distributions. In class, what have you guys started with this?
One lesson.
Okay.
You just like Z school formula and all
I could look at graphing.
It's very weird because for me, I do that at the end.
Oh,
I do the rest of the probability distributions topic, then I end off with normal distributions. I just feel like it fits better that way. So let's just do it my way. And yeah, and if you guys are learning something in class, it means when you guys do cover this, it'll be a bit easier. And then when we get to that normal distribution, that'll be easier with me as well. Fair enough? Okay, so continuous probability distributions. Now, back when we were studying for trials, we went over a lot of this stuff. Like we had like a little class where we were, because the beginning of this booklet is a revision of year 11 probability.
yeah.
Right? So I'm going to kind of, you don't need to read word for word everything on here because it's a lot of words. It was like, it's meant to just be, you guys just revise all of this for your trials. So you can know all of this stuff already. But just some main key points that we need to be able to move on with, all right, for the rest of the topic. So in year 11, we had two probability topics. We had probability in Venn diagrams with all the A union B, A intersection B nonsense. And then we had the discrete probability distributions. So expected value of X and variance of X and that stuff. This topic is the second part to probability distributions. Instead of discrete, it's now continuous. Okay? So where in year 11, we dealt with like rolling a die, having outcomes 1, 2, 3, 4, 5, 6, where the outcomes were discrete. In year 12, we're trying to model a continuous variable. So like someone's height, right? Or the amount of time taken for something to happen, because height and time are continuous variables. Okay? So what have I got here? A lot of words, a lot of words, a lot of words. Nothing really relevant there, but let's just come down to here. So the different types of variables and types of variables and outcomes. So when dealing with data and probability, the types of variables and outcomes can be split up into two branches. Firstly, whether they are categorical or numerical, and then sub-branches as well. So we have categorical, numerical. So categorical variables are variables which are words, okay? They just represent different categories or subgroups. And then numerical is where the outcomes are numbered, okay? So in terms of the categorical, they get split up into two other branches, nominal and ordinal. Nominal is where the outcomes have no inherent order, okay? So like an example of this is race, because there is no order to race. Someone being, Italian or Arab, there's no order. Maybe some people think there's an order, but there shouldn't be an order, okay? And then ordinal, I should have chosen a better example than race.
Yeah.
I
thought you were talking about like an actual race at first, and I was like,
oh no, sorry.
And then you were like, oh, okay.
Maybe what's not like eye color.
Yeah.
Eye color, there's no order to that, no inherent order. Maybe a subjective order, like blue or green eyes, like number one. Yeah. Okay. And then ordinal is where there is an order, right? There's an inherent order. So like the grade you get in an exam, like an A, B, C, or D, or an E, or whatever, or whether you get like, on your grade, your reports, how you get commendable, achieving, and needs improvement or satisfactory or whatever it is. So there's an inherent order to those. Whereas your numerical, you can split those up into sub-branches. We have discrete and we have continuous. So all of them are numbers, but a discrete random variable. It's not necessarily only whole numbers, but you're right. Whole numbers are discrete. But the idea is that they're just fixed numbers. Okay? And numbers in between those fixed ones don't make any sense. Yeah. So for example, saying how many students do you have in your class? That's a discrete variable because you can't have half a student or like a third of a student or like pi students, right? But what about shoe size? Shoe size is like 9, 9.5, 10, 10.5.
Mm.
You have halves, like you have 0.5s, but to say 10.133 doesn't make any sense, does it? Right, as a shoe size. So that's still discrete, because even though you have decimals, anything in between those decimals is like has no logical meaning. Okay, no contextual meaning. Whereas continuous doesn't matter how small or how big or how many decimal points, it all makes sense. Like to say something is like continuous is like time, right? You could have an hour, you could have half an hour, you could have a second, a millisecond, a nanosecond.
Yeah.
You could have 5 nanoseconds, you could have pi seconds, all of that works, right? What's other examples of like of continuous variables? Distance, speed, even money. Even though money usually it's like two decimal places for cents.
Yeah.
Technically money can be to like an infinite number of decimal points. It's just that we never transact with it ourselves on a day-to-day basis. To that many. What about ATAR? Is ATAR continuous or discrete?
Wouldn't it be discrete?
It'd be discrete. Because even though you can go to the second decimal point, 99.15, 99.85, you can't go any further. Like to say 99.02 doesn't mean anything, or 99.005 doesn't mean anything. Fair enough? Oh, here we are. Eye color, country of birth, brand of car, these are all nominal. There's no order to them. Whereas ordinal ones, educational level, high school, bachelor's, master's, PhD, customer satisfaction, and then your grade on the exam. Numerical, we have discrete, the number of siblings a person has, the number of items you sold, the outcomes of a diagram. Whereas continuous, we have height, weight, and time. Technically, this weight should not have a square bracket there, should be a curved bracket, and time should also be a curved bracket. I put height 2.72 because I Googled this. The tallest ever person was 2.72 meters. So I put that as the maximum. But even technically, that can go to infinity because unless I wrote height of humans, I mean, maybe someone can even pass 2.72. I don't know. Two of me. Not two of me would be that. I mean, that's not a flex.
How much is 2.72 in feet?
Oh, 1 foot is 30 centimeters. So it's probably around 9 foot, I think. Because 9, yeah. That's crazy.
Is he still alive?
No, he died. He only lasted 22 years.
You lost it.
Well, I mean, like,
He's as tall as the basketball ring. He wouldn't even have to jump.
do you think there was basketball back in 1918 to 1940? Yeah.
Yeah, nice. Yeah, there is.
When did the NBA start? Was it the 50s?
Sometime around towards the 1940s.
Ah. He only lasted 22 years.
So
He's one of those, he's like a star with like a very bright burn, but doesn't last that long.
yeah.
All right.
But
But then again, if we think about it,
yeah.
he only lasted 22 years, but he had the height of like 2 times other people, you know, or maybe not 2 times, definitely 1.75 of other people, right? So if we divide 22 years divided by 1 point, let's say 5, sorry. Even though he only lived for 22 years, that's equivalent to living for 33 years for a normal heighted human. Because, you know, he had 1.5 times the height of a normal person. So if we think about it like that, he lived a longer life. Still not that long, but whatever. And the current tallest person is 2.51 meters. Some Turkish guy, I think. Yeah, nice.
What's his name?
Which one? The tallest one? Robert Wadlow. And the other one, the one that's currently living, is Sultan Kösen.
Pretty cool.
Yeah. Fun facts. Okay. So again, in year 11, we spoke about discrete random variables. And part of discrete random variables are your probability mass functions. Remember, we usually denote our probability mass functions with like a table. We say here's X, here's all of the outcomes, and then here's P of X, all of the probabilities of those outcomes. And from that, we were able to calculate like a bunch of things, right? where we calculate expected values, variances of standard deviations, sometimes the median, the mode. Yeah, that's it. And the probabilities. I forgot about that part. Okay. We know a few components from this, or a few identities. First, every probability should be between 0 and 1. True? True. And then the sum of all the probabilities equals 1. And as we saw in a bunch of practice exams, if you have an unknown probability, you can use the fact that the sum of the probabilities has to equal 1 to like work backwards and find out what it is. The reason why I'm writing this here is because we have similar approaches for continuous variables. Okay, it's just that we need to interpret what it means in a continuous context. Fair enough? Stop me if you feel like I'm rushing over anything. Yeah. Expected value. We know what the expected value means. It's mean, yeah. Basically, it's what we expect to occur, or we should expect to occur on average, right? It's used to summarize the central tendency of your random variable. Okay, so if you have like this is how we calculate it. The expected value of x is given by sigma x times p of x. Okay, often also referred to as mu, right? So for example, if we were paid the outcome of a die roll, that is, if we rolled a 1, we would expect to be paid $1, 2, we would get $2, and so forth, then what amount of money are we expected to make? So the random variable here, which we can denote by capital X, corresponds to the amount of money we would be paid and has a following P amount. So X, P of X, and you just do 1 times 1 on 6 plus 2 times 1 on 6 plus 2 times 1 on 6. And you get 3.5. Which means you would expect to make $3.5 on a die roll. But you can't actually make 3.5 on any die roll because it's not an outcome. It just means on average, that's how much you make. Okay. Perfect. Here are these two properties. Do they pop up in your trials? No? It's just the fact that you can break up the expected value into the expected value of x, like expected value of x plus y, where x and y are both variables, can be split up as the expected value of x plus the expected value of y. I barely ever see these show up, right? But this one could pop up in like I don't know, have you seen it pop up in a trial? Not really. Like they tell you like the expected value of x is equal to 4, and they say find the expected value of 3x plus 2. Oh, really? No? Damn.
So you can just break it up. That's all it is.
Yeah, you can make this 3 times the expected value of x plus 2. So then it's going to be 3 times 4 plus 2, which is 12 plus 2, so 14. Okay. Yeah. I don't really know what to say. It could pop up, so I would know it. But yeah. Okay. We did this example before, so we don't necessarily have to do it because it's not even relevant. I just need you to ensure you know the formula. That's the main thing. The median. Don't worry about an example for this, but the median is the 50% mark, which means the probability that x is less than or equal to that median outcome has to be 50%. Okay, so if you have a die roll, let me copy this in again. It's the middle. Where's the point where we're in the very, very middle? Where there's 50% to the left and 50% to the right.
3.5.
3.5. So you find the point where it's probability that x is less than probability that x is less than or equal to 3 is 50%. But the probability that x is greater than or equal, greater than or equal to 4 is also 50%. So surely it's somewhere in the middle between those, and usually we just take the average between it.
I think there's a thing in normal distribution or whatever. We did it yesterday, not yet, Friday.
Yep.
Where the mode and the median and the mean are all the same.
Yeah, that's right.
So is that for is that what x is? No. Yeah. Middle.
The middle. But that is for a specific distribution called a normal distribution. So we haven't gotten to that part yet.
Yeah.
Okay. But yeah, you're right. That one, it all lines up at the same point. Okay. Your mode is just your most occurring score. Now, which one's going to occur the most? The one that has the highest probability. Kind of makes sense. Yeah, if like there's a 99% chance that you're going to land on heads, what do you think is going to show up the most times? Heads. That's it. Okay. Then variance and standard deviation. We know this is a measure of spread. Higher variance means that our outcomes are more likely to be, we're more uncertain about our outcome. Lower variance means our outcomes are more consistent. The way we calculate variance is we use this formula here. And remember to find the expected value of x squared. It's sigma x squared times p of x. And the mu is the mean, which we already know. It's sigma x times p of x. Fair enough? Those two properties for mu and for variance are true as well for continuous. Okay, so we're going to just follow that through. Here are some properties about variance, but again, you don't have to really worry about these ones as much. You do kind of have to worry about this one.
Yeah.
The variance of ax plus b is a squared times variance of x. So if I told you the variance of x equals 4, and I want you to find the variance of 3x plus 2, then this just equals 3 squared times variance of x. So let's kind of break down why that's the case. Okay. I'm going to use the generic form, variance of ax plus b.
Are these formulas in our formula sheet anywhere? Because we've got continuous random variables.
No.
So what are these ones for then?
Those ones, we're going to use those. Yeah.
Okay.
If you've been given the variance of ax plus b, first of all, one of our variance properties is that I can split up the sum as long as the two events are independent. Remember, a and b are constants. Okay. So if x is some variable, and a is just a multiple of the variable, and b is just another multiple of the variable, b is not an event. B is just a number. So I can split it up as variance of ax plus variance of b. So if we do that for here, this one would have turned into variance of 3x plus the variance of 2. Now, variance is a measure of inconsistency. How inconsistent is this variable? How inconsistent is the variable 2? 2 is a number. It's not a random variable. Like if I say like, how uncertain are we about the value of 2? We are not uncertain about it. We are 100% certain about it, right? It's not like how uncertain are we about the outcome of a die roll where there's uncertainty there. But how uncertain are we about just a number? We are not uncertain. The variance of the number is just 0. Okay. So this one just equals 0. So again here, variance of b, if b is just a constant number, this should just equal 0. But if we remember how to calculate variance, it's expected value of x squared minus mu squared. Everything is squared for variance. So that's how I remember that when you take it out, you shouldn't just be taking out an a, you should be taking out an a squared because everything is squared in this. That's how I kind of reasoned this myself. So even here, when you take out the 3, it should be 3 squared, just because everything in variance is a square term. So that's a way for you to be able to derive that without really having to memorize it. Actually, I may as well, while I'm here, show you the derivation for the expected value one as well. May as well, right? Is that kind of reasonable? Okay, what about the expected value of AX plus B? And again, we'll do the expected value of 3x plus 2. Expected value, doesn't matter whether they're independent or whatever, you can always split up an expected value. Okay? The proofs for that are kind of way beyond this course, so we don't have to worry about that. Okay, just take my word for it. Even here, this is expected value of AX plus the expected value of B. Now I want you to look on the right-hand side over there. Expected value is like, what do I expect the value of this thing to be? What do I expect the value of 2 to be? 2. So again here, what do I expect the value of B to be? If B is just a constant, it should just be B itself. Does that make sense? And expected value is not a square term. So what's the expected value of 3x? It should just be 3 times the expected value of x. So here is the expected value of AX should be A times the expected value of x. Okay. This app has a new update where I can write as if it's a pencil. Doesn't that look more like, if I compare that to, I don't know, I feel like it looks cooler.
It's the same thing.
Fine. Okay. All good? Okay, that's the revision, right? I feel like we didn't,
That was revision.
yeah.
That else.
Oh, that last stuff is like a reminder of like how you get to those properties, but those properties show up in year 11 as well.
Yeah.
Okay, but in terms of like expected value, variance, standard, like all of that stuff,
Yeah.
yeah. We just now need to transform this all for a continuous distribution. Okay, so now everything here is new. A lot of words, but it's all important. So a continuous probability distribution is a probability distribution that describes the probabilities of outcomes or events for a continuous random variable. They can be used to model the movement of stock prices, the time taken for certain events to occur, as well as the severity of different events. Their applications extend to the fields of economics, physics, and engineering, as they allow for the analysis of continuous phenomena which have an infinite range of possible values. Okay? In a continuous probability distribution, the probability of obtaining any specific outcome is infinitesimally small, since there is an infinite number of possible values within a given range. So instead of assigning probabilities to individual values, continuous probability distributions assign probabilities to intervals or a range of values. Now that's like an intro, it doesn't really make much sense, but the whole next 2 pages try and explore what that means, okay? For example, let's say we're trying to model the heights of males in Australia. We can't assign a separate probability for each possible height because there's an infinite number of heights, right? Continuous distribution, if it's a continuous variable, that variable, as we kind of spoke about before, can take on an infinite number of outcomes. It's not like discrete where your ATAR is fixed to be this, or this, right? Like I could have a height of 172 centimeters. I could have a height of 173 centimeters. But I could also have a height of 172.5, 172.51, or 0051. You know what I mean? So how am I going to create a table with all of the infinite number of options and with all of their own probabilities? There's an infinite number of outcomes with an infinite number of probabilities. Does that make sense? So I can't go around saying, here's the probability of being 172 centimeters.
Yeah.
Because for me to be exactly that is very, very unlikely. Like my height is 172, okay? But Is it exactly 172? Probably not, right? I mean, almost definitely not. But let's say let's say I have the most accurate ruler and I end up being 172.0000001,
Yeah.
right? Am I gonna then go and have to like what's the chance someone else is the exact same height as me?
Very.
Like very infinitely small. Okay. So for continuous distributions, we say the probability that the random variable takes on any exact value has to be 0. The probability that someone is exactly 172 centimeters, 0. Probably someone is exactly 173 centimeters, 0. Right? Because I shouldn't be defining probabilities for every exact value. Does that make sense? You might say, what if I say probably that someone is 172 centimeters to the nearest centimeter? Yeah, that's fine. We can find a probability for that, but then it no longer becomes a continuous variable. It becomes discrete because now I only have 172, 173, 174 because it's all to the nearest centimeter. Does that make sense? Perfect. So that's what that middle paragraph says. So instead of using probability math functions, which mean I need an infinitely long table, we have to instead use something called a probability density function to model these variables. Okay? That's what your z-score tables are all for. That's all based on a density function, but it all makes sense in a moment. Okay, so the probability density function, or PDF, for a continuous random variable x is a function usually denoted by f of x. I want you to ignore. Let me get rid of this. I use subscripts because it's more accurate, but then I found that it's really confusing with all of it. So I should have gotten rid of all of this. Okay. So if you have a random variable x, like x could be, I think I've given an example here. X could be the random variable, which corresponds to the length of time a certain smartphone's battery lasts in hours. It can be expressed by the following hypothetical. This is the first draft of the booklet, so please don't judge. Can be expressed by the following PDF. Now I just made this up, right? This is a PDF, a probability density function, which tries to model how the probabilities behave for a smartphone's battery lifetime. Okay?
Yeah.
And I just made it up, but let's break down what this function actually says. So firstly, the lowercase x represents the possible outcomes the random variable can take. That's true even for PMFs, right? Like, you know how we do sigma x times p of x and we use lowercase x's? That's because it's for the outcomes, isn't it? Same thing here. I've used lowercase there because it's the outcomes. For example, x equals 70 means the smartphone's battery will last 70 hours. If you look at this piecewise function, for x is less than 0 and x is greater than 100, the PDF is defined by 0. This means that the random variable is not defined for battery lives less than 0 hours or more than 100 hours. Or if you put it differently, there is a 0 probability that the battery lasts less than 0 hours or more than 100 hours. Of course, it's impossible for it to last less than 0 hours. And then for whatever reason, this battery, let's just say like, it's impossible for it to pass 100 hours. I don't know, like it has a kill switch. If it gets to 100, it just turns off. Okay? Now, PDFs often given by these piecewise functions will have an interval like the 0 to 100 one that's provided. In this case, it means that the only possible battery lifetimes the smartphone could have are between 0 and 100 hours inclusive. For this interval, the PDF is defined by the function that we'll mostly be dealing with. The zeros are irrelevant, but that middle function is the important one. Okay, so let's kind of figure out what this function tells us. So it provides us insights into how the smartphone battery will last with time. Now, I mentioned this before about how we can't find probabilities of exact outcomes. Even if we have this PDF, I'm not allowed to say, I wonder what the probability is that the smartphone will last 2 hours. I can't just sub in 2 hours like I've done here, okay, and then say it's that, and then that's 1.96%. I can't say the probability that the smartphone's battery lasts 2 hours is 1.96%, because I also could have subbed in 2.1 and 2.001 and 2 point whatever, okay? So the probability, if someone asks you, what's the probability that smartphone's battery lasts exactly 2 hours, you will not sub anything in and you will say 0. Like the chance it lasts exactly 2 hours, that's 0, basically, right? Okay. So subbing into the PDF is almost fully useless. The only thing it's good for is to compare probabilities. Okay. So you might sub in x equals 2, and you might sub in x equals 40, and you might say, oh, 2 gives me a bigger number than 40. That means I'm more likely to last 2 hours than I am to last 40 hours. But the number you get as a number itself means nothing. Is that okay? Because sometimes the number is more than 1. Like it doesn't even, it's got nothing to do with probabilities.
Yeah.
Fair enough? So yeah, if PDF cannot give us probabilities of exact outcomes, what is it even good for? Yeah, I just spoke about the comparison part. Okay. Yeah, I'm giving here like in our example, f of 65 is greater than f of 85. The actual value doesn't matter. It just means it's more likely to last 65 hours than it is to last 85 hours. Okay. You can also look at the plot and you can like get a trend about where it's more likely to be just by looking at how the y values, like where they're higher and lower. But again, the y values mean nothing other than for comparison. Okay. But what can we actually do with our PDF? Well, interestingly, even though the y values don't matter, the area underneath the curve does matter. The area underneath your PDF corresponds to probabilities. So I think pretty cool. So the curve doesn't matter. Like the y values don't matter, but the area underneath is a probability, a legit probability.
So that's where the calculus comes in.
Yes. So what's interesting is like, I can never tell you the probability the smartphone will last 65 hours. But if you ask me what's the probability the smartphone lasts between 60 and 70 hours, we can actually calculate that probability. Now you might say, what if I really want to find out if it's going to last 65? Okay, do 64.9 to 65.1. If you do a range, you're fine. You can get the probability. Okay, but just exact values it will never give you. We also have this thing called the cumulative distribution function, the CDF. That also has something to do with the area underneath the curve. We can find the expected value or the mean. We can find the median. We can find the mode, and we can also find the variance and standard deviation. So everything is based on this function. It's like a I can't remember the hypothetical. I don't know. What's a hypothetical of like something that's useless, but you can manipulate it to make it useful? I don't know. Is there anything?
What?
Like anything where like it itself is useless, but you can like manipulate it to make it useful.
Flour,
What?
baking flour.
Baking flour, true. You can't do anything with baking flour, but like could make cakes and stuff. But you would never eat the flour. Like I don't know, like kids. Like kids are kind of useless, but you can
Okay.
manipulate them, like bribe them with like chocolate and lollies,
Yeah.
and then I mean, what do they do then for you? They don't do anything for you either. Maybe kids are just useless with no redeeming qualities.
Yeah.
I don't know. Do they? What's a kid useful for?
You just love it, right?
Getting
It's
into
like-
tight spaces.
That's true. Yeah.
You know, we have this thing called in the legal system. If any of you guys do legal studies,
Yeah.
I forgot the name. It's like some Latin term. It means that kids under the age of 12 are incapable of harm or incapable of doing wrong. No? Let me find out the name of it. Wait,
Like maybe they don't like actually need it, but
Dolly Incapax. Yeah, that's it. The minimum age of criminal responsibility in Australia.
yeah, like because they don't need it, like they don't really know what they're doing still.
So if a child is under the age of 14, oh wow, that's kind of high.
Yeah,
Then they considered to lack the capacity to be criminally responsible for their acts. So I guess kids can be useful that way. Like if you just direct them to do your crimes. Yeah, oh, that's a good one. So now it's a useless, like a PDF, where you can manipulate them
Yeah.
into committing crimes for you, just like how you can manipulate the PDF.
What if they snitch on you though?
Yeah, but you're telling me you can't like you can't manipulate the kid enough to like not snitch.
Oh,
Like if you scare them, I don't know.
I'll spill your chocolate if you.
Yeah, if you tell me if you tell them who I am. So probabilities and areas underneath curves. That's kind of what I was talking about. All right. The PDFs are only useful for calculating probabilities if the random variable takes a value from a region or an interval. For example, even though the PDF can't tell you the probability that the smartphone's battery lasts exactly 65 hours, it can be used to determine the probability that it lasts somewhere between 60 and 70 hours. When we had discrete random variables, if we wanted the probability of a range of outcomes, we would simply add the probabilities of all the discrete options, okay? But now that we have an infinite number of outcomes, what's the infinite version of a sum? An integral, right? So if you want to find the probability that the smartphone's battery lasts between 60 and 70 hours, you're basically taking the area underneath the curve from 60 to 70, okay? And that's exactly what I've done here. Don't worry about that little x. Again, that's my bad. You're just integrating this function, your PDF, from 60 to 70. And of course, the PDF is given by that.
So do they, in your questions, do they actually give you the PDF?
Yes, yeah.
They do?
Yeah. Sometimes there'll be like an unknown in the PDF or something like that.
You gotta find
And
it.
you got to find it. But for the most part, like the main chunky part of the curve is given to you. So by the way, like this PDF, it's a linear equation and kind of looks something like that. 0. I really don't care about the y values, so I'm not even going to put the number there. Okay. What we're doing is we're finding the area from 60 to 70. That there is the probability that x is somewhere between 70 and 60. This probably will correspond to the following area. That meant I was supposed to insert this diagram. Does that make sense? Yeah. So like now, what can we say generally? Like if you want to find the probability that x is between any two values, all you've got to do is take the integral from a to b of your PDF. That's it. Now I was in second G uni and there was some kid in my like actuarial class and he wasn't understanding this, which is kind of crazy because like he's supposed to be an actuarial student, right? I don't think he lasted that long in the degree, but anyway. But my tutor was like, he wasn't getting this idea. And then my tutor said, I don't understand what's so hard. If you just think about probability being the area underneath the curve, there's nothing really to like be confused about. If you want probability that you're between 60 and 70, find the area underneath the curve from 60 to 70. That's it. If you want to find probability that you're anywhere more than 50, well, if you're from 50 and you can only go to 100, find the area of under the curve from 50 to 100. Yeah, you know what I mean?
Yeah.
Yeah. Like, what if I wanted the probability that x is less than or equal to 15? Where would I be taking the area from? Like, here's your function, and I need to be less than 15. Wouldn't I just integrate? Wouldn't I find that area there? 0 to 15. That's it. From the starting point, wherever it is.
But how do you
15.
know X is from the start? Like, you know what I mean?
If it's just x is less than or equal to 15, you look at your original PDF
Yeah.
and you say, like, the smallest value I can take, what's the starting point? 0.
Oh, so you just take the starting point. So that's okay.
Exactly. Like, what if I had said, the probability, so this is gonna, sorry, let me write this in here. This would equal the integral from 0 to 15, like the function. What if I had put probability x is greater than or equal to 80? Where would I be integrating from? And to where?
80 to 100.
80 to 100, like from 80 to the very end.
Oh, so you just look at the sign and it basically determines if it's from 0 or 100.
Yeah, exactly.
Yeah.
Plus a quick sketch, your sketch doesn't have to be super accurate. Even if you just went and drew something like rubbish. Oh, don't make it look straight because that's kind of dodge. Even if you make it something like that. All you need is to say like, oh, 60 to 70, that area there. That's it. Doesn't matter whether your curve. I mean,
Right.
ideally it should look like it because it might give you some insight.
Yeah.
But a rough diagram is good enough. Yeah. Any questions about this so far? Probability, area underneath the curve. That's it. Oh, actually, I do have a comment. How would this be different to, so we spoke about how that there is given by this integral here. How does this differ from the probability x is between 70 and 60, but not inclusive? What do you think? I don't think it matters. I think these two are actually equal to each other. The reason why I think they're equal to each other is because what's the probability that you actually equal 70? What do we define that as? 0. We said the probability that you equal anything exact is always defined as 0. So the probability that you equal 70 is 0. Probability that you equal 60 is 0. So the probability that you actually, the all equals component makes no difference to the inequality. It makes no difference to the region. Fair enough? So these two are equal to each other. Even if you say something like the probability x is less than or equal to 15, that's equivalent to the probability x is just less than 15. Doesn't affect how you, like, does the area under the curve matter whether you include 15 or not? No, because that's an infinitely small number. Yeah. Approved? Okay, let's do this example. The random variable x represents the time in minutes taken until the train arrives at a particular train station, and it has the following probability density function. By the way, this is how we actually model time for a train to show up. Like, this is called an exponential function. Well, I mean, you know, it's an exponential, but there's a certain type of distribution called an exponential distribution. Anyway, so for what range of times is this random variable defined for? I'm trying to interpret this and this.
What, like?
I would actually just say x is greater than or equal to 0.
Yeah.
Like, if we look at the way that the PDF is written, for x is less than 0, it's undefined. It's just 0. What's the chance that the train shows up in negative time? That doesn't make any sense, does it?
Yeah.
Right? So, but what we have is we have a function for when x is greater than or equal to 0. So it's saying, what range of times can the train show up? Well, it can show up like instantly right now and any time into the future. And technically, it can show up like an infinite bound, right? All right. So for any times greater than or equal to 0 minutes. B, sketch the PDF on a Cartesian plane. It's a negative exponential, isn't it? Bit of a throwback.
We just like that way, I think.
Like this way?
Yeah. So that.
That's if it had a positive power. But it should be the other way around.
Oh, yeah.
It should be
so maybe,
like that.
yeah.
That's it. If they had asked you in an exam to sketch it, you should probably show the y-intercept. Not that I care about the y-intercept, but if you're asked to sketch it, you should probably just show it anyway. The y-intercept ends up being 0.08. But again, that's not a probability. That's just a number. Okay. What is the probability that the train comes within the next 15 minutes?
So do you do the like area under the curve from like from 0 to 15? I guess.
Yeah, exactly. Again, I put the all equals for those. Does it really matter? No.
And so how would you know if it's coming from this graph, like the graph is like from 100 to like 15 or whatever, you know what I mean?
You just have to read the question and try and make sense of it. So we're gonna have a bunch of practice with this. Like you got this one right.
Yeah,
It's within the next. So like anytime now till 15 minutes.
that's what
Yeah, perfect. So let's just sub this in and then we'll talk about it more. Negative e to the minus 0.08 times 15 minus e to the negative 0.8 times 0. Second one all goes to 1. We can write that as 69.88%. So there's your 69.88% chance likely for the train to show up within the next 15 minutes, which is pretty high. Okay, what about the next one? What is the probability that the next train takes between 35 and 50 minutes?
I
Yeah. Now, just based on the graph, 35 to 50 is the same interval. 0 to 15 is 15 minutes, 35 to 50 is 15 minutes. Do you think this should be lower or higher than 69.88 based on the areas underneath the graph?
Small.
Should be smaller, yeah. It should be way lower than the 69.88.
I got negative.
You did?
Oh, wait, I didn't know.
You should not have gotten one, I don't think.
Yeah, now because I put it in I got 0.042.
Yeah.
No, because I put the 50 and the 35 in the wrong way.
Oh, okay.
Yeah.
Yeah.
What a constant.
So it's only a 4.25% chance.
Yeah.
Okay, that makes sense. By the way, this distribution is pretty cool because it's actually irrespective of when the last train showed up. So imagine if you walk to a train station and all of the TVs are turned off, right? You don't know when the last train came,
Yeah.
and you don't know, and obviously you're waiting for the next train, right? If all you know is on average how many trains show up every hour, you'll be able to calculate these probabilities, which is pretty cool. I mean, you don't know how to do it because you haven't covered this, but like this is what like I've covered before. Which is
So if I went to the train station and so without a math textbook, the train time.
yeah, like if for example here, the way I built this question was that trains show up every 12.5 minutes. That's the way I did it. On average, every 12.5 minutes. So if all you know is trains show up every 12.5 minutes,
Yeah.
what's the chance it shows up within the next 15 minutes? 69.88%.
Yeah.
What's the chance it doesn't show up for 35, but then shows up within the next 15 minutes after that? 4.25%, which kind of is reasonable because if trains show up every 12.5 minutes, by the time 35 minutes have passed, almost 3 trains should have come. So the chance that the train doesn't come until then should be very, very low. Okay. What is probably the train takes longer than 20 minutes? So if you're trying to find the probability that the train lasts more than 20 minutes, where are you taking the integral from? 20 minutes to infinity.
Oh, infinity.
Mm-hmm. Now, advanced doesn't really deal with integrals to infinity.
I'll probably just move like 100 or something.
Well, the 100 comes from the previous question, right? But because if you look at the way the original PDF is defined, it's just defined for x is greater than or equal to 0. So technically it is 0 to infinity.
Yeah.
Okay. So I'm going to show you how to do this using infinity, but I'm going to show you another way which is you might be more convinced of. Okay. So I'm not going to put infinity there. I'm going to put an R there. And I'm going to, because I can't really put infinity and sub-infinity in because infinity is not really a number.
So can you just put like a really large number in?
Yeah. But that's like cheating the notation. Okay. So I'll show you this. What I would do is I would take this thing here. I'm taking the integral from 20 to R, but R approaches infinity. Because that's like better mathematically to write. Okay, like I can sub in R's just fine. So what is it? 0.08 e to the minus 0.08 x dx. Integrate this as per usual, but keep writing this limit at the front. Again, it's the exact same one.
Yeah.
And now I'm going to sub in R and 20. Minus e to the minus 0.08 R minus e to the minus 0.08 times 20. Now I want you to think, what should this go towards when R approaches infinity? From 0. Yeah. And that's Dion, that's done by subbing in a big number.
Yeah.
Yeah. So like if you want to convince yourself, you just take this and chuck in like 1,000 or something. Even 1,000 is probably just going to give you 0 automatically. But if you chuck in like 10 and then a 20 and 30 and 40, and you see it get smaller and smaller.
Yeah.
And then yeah, eventually it'll just rush it to 0. Perfect. So this ends up being 0 plus e to the minus 0.08 times 20. And we can find out what that is. Because the first one goes to 0, but the second one stays.
Yeah.
What's another way we could do it? We could say the problem, so we don't have to go to infinity. We could use complementary property and say probability x is greater than 20 is equal to 1 minus the probability that x is less than 20. By the way, you know, I didn't put all equals for either of them because it doesn't matter. Technically, that should have an all equals there.
Yeah.
Because like I'm saying greater than 20, the other one should be less than or equal to 20, but the all equals doesn't make a difference. So that's why I forgot it. Okay, and probability x is less than or equal to 20.
I see just -1 minus 20.
Well, I find that area there, because that area there is probability x is less than or equal to 20. We're not going to do it because that's just another integral, but it'll be 1 minus, and then this is the integral from 0 to 20. But this should, again, in the end, give you the same 20.20%. Is that okay? Perfect. Any questions or concerns about this? No? So now I want you to consider a generic probability density function for the random variable x. Let's say it's f of x is given by some PDF for only the interval a to b, and then it's not defined for any other values. So this a to b just means that the random variable can only take values between a and b. Like the smartphone one was 0 to 100. Okay. Now, in order to have a valid probability density function, two properties must be satisfied. So, comma, two properties must be satisfied. Just as we had two conditions for a valid PMF or a probability mass function, we have similar conditions for a PDF. So for a PMF, we said each probability has to be between 0 and 1. And we also said that if you add up all of the probabilities, it should equal to 1. But when we have a PDF, density functions, we found out that the actual Y value doesn't matter that much. So the only restriction on the Y values is that they're greater than 0 or equal to 0, okay? The function that you have should always be above the x-axis because a negative density doesn't mean anything. But the density being more than 1, who cares? Because that Y value, the height of it doesn't make a difference. Is that okay? Yeah. So f of x has to be greater than or equal to 0. Despite f of x values themselves not having much meaning, having negative likelihoods, which is what f of x really tells you, is impossible. And thus the function could never be below the x-axis. That's the first condition. The second condition is that, you know how for a PMF, the sum of all the probabilities has to equal 1? Like sigma p of x has to equal 1? The continuous version of sigma is an integral. So if you integrate, you find the full area underneath the curve, it should equal 1. That makes sense as well. Like if you're going to find the total probability, it would equal 1.
So they're going to like do the same sort of thing as like year 11 where they don't give us a value, you gotta like find it.
Exactly. Or they might say something like, confirm that this is a valid PDF. So confirm means you got to do two things. Sketch the curve to show that it's always above the x-axis, and integrate it and show that the area is equal to 1. Okay? So like if this was your function, I don't know, here's A, here's B. Say it's there, and let's say it's there, and it does like whatever this is. Actually, we'll do another one. But this is something called a survival function. Yeah, it talks about how likely you are to die at different ages.
Oh, damn.
Yeah. So it starts off like high because you might have infinite mortality. Then you start to get into your shenanigan era, right? So like your teenage years, and then the likelihood kind of goes up. Actually, I think, let me draw this bit better. It's high, then it goes down, and then it goes back up. And then it goes down, then it does that. Bit better. Because
the higher you are, like, the more likely you are to die.
yeah, at that age. So you're pretty high infant mortality, then it goes down when you're like 9 years old, you don't do anything wrong. You know, Dolly Incapax. And then you get to like 15, 16, and you become a hooligan. And maybe to 21, I don't know about my peers. And then it drops again because you become a responsible adult. And then you get old and it just goes up. Okay, so this is your like a PDF. All that we need to ensure for this PDF to be for it to be valid is that this full area underneath the curve is equal 1. Okay, that ensures it's a valid PDF. That's right, valid to you. Pretty cool, right? It's kind of grim. I have to actually learn about this stuff at uni. Luckily, I finished all those courses, so now I no longer have to worry about survival modeling.
What would you even need that? Like, what would you need that for?
For insurance. So I didn't know this before doing the degree.
So like, do they make your insurance more expensive? Like, I wouldn't be like,
Yeah. Because what is life insurance, right? There's two forms, but the most obvious one is, let's say me, I have, I have a family in like let's say 40, right? I have a
Yeah.
family and they're relying on my income to survive. If I die, I won't get any income. And then what's gonna happen to my family? They're gonna need the money, right?
Yeah.
So if I take out a life insurance policy under my name, in the event that I die, they'll be able to pay out my family what they would predict how much I would make up until the day I retire. So let's say I retire at 65. They might say like, well, currently he's earning, let's say 80 grand a year. With inflation and with growth, maybe he gets this sort of raise or something like that. He'll make around this much money, and this is how much we pay out to them every year.
Jesus, that's like, would that be expensive life insurance?
Depending on who you are and the type of life you live.
Okay.
Like if you're a 40-year-old and you smoke and maybe you dabble in some drugs, then
I know about it, that'll make it expensive.
yeah, they might not even insure you if you dabble in drugs.
Really.
But if you have like other health defects, yeah,
It's kind of sad. What happens if you're like, what's it called? Like, I don't know, you're a good person, yeah, but then you get like something bad, like cancer or something like that. Then
Mhm.
what? Like, do they just not take you on?
unfortunately, yeah, no.
It's pretty sad.
It is very sad. It is very sad.
Yeah.
Yeah, it's quite
Yeah.
sad. That's why there's like the government kind of steps in when like, because it's a private company, right? Like an insurer is not the government, an insurer is a private company and they're trying to make profit.
Private one.
So why would they do something when they know they're going to lose money on it?
Yeah.
That's when the government's technically supposed to step in, which they kind of do. Maybe it's not enough, which I don't think it's enough,
Yeah.
but that's kind of their role. At least that's how current economists perceive the matter.
Yeah.
But there's actually another type of insurance policy. So one is if you die too early,
Yeah.
because then you can't afford to pay out your family. By the way, you can even say like, I want them to be paid out $2 million. Maybe you won't even make $2 million in the next 25 years, right? Or 3 or 4 or 10 million. No one puts a cap.
Yeah.
But if you told them, like, let's say I made 80 grand a year, and I'm like, I want my family to be paid out $10 million. The insurer is going to be like, okay, yeah, sure, whatever. But do you know how much you have to pay every month to have this insurance policy? It's going to be so much where I can't even afford it on an 80 grand salary. So
Yeah.
technically there's no cap on it. But there's that one. That's the most obvious one. I didn't know that there was actually another type of insurance called longevity insurance. So one is if you die too early and you can't afford to feed your family.
I guess longevity is like you can't work anymore.
Yes.
Like, yeah.
So you die too late. Basically, it's if you die too late where you get to the age where you use up all of your savings and you can no longer work because you didn't think you would last this long. And now you need money.
Some LeBron James like shit.
That's crazy.
So yeah, basically there's a big industry in longevity insurance now because people are living longer.
Yeah.
And people would maybe not able to work for as long into their lives.
Yeah.
So you can take out longevity insurance. Yeah, pretty cool. I would never work in it, but it's pretty cool. Okay, nice. So we have those two properties. Area underneath the curve has to equal 1. And just like how with PMFs, we can use that property to find unknown value. We're going to do the same thing for PDFs. Getting all these acronyms confused. Okay, so here's this. The random variable y is attempting to model the daily percentage change in the share price of Apple. For example, if y equals 1, this means that the share price of Apple has increased by 100%. This is not unlikely, right? The random variable y is defined by the following PDF. So f of y, I'm not using x's here, just as a different example, is equal to some constant times 1 minus y squared, and y is only defined from -1 to 1, which means on any day, the percentage change in Apple could be 100% or minus 100%. So it could either double in price or lose 100% of its value and drop to 0. Okay, so the first question is find the value of C. Well, if it's a valid PDF, then what should the area underneath the curve be? Should be equal to 1. And where are we going to integrate from?
-1 to 1.
-1 to 1. So the full range in in where the PDF is defined. So some constant times 1 minus y squared dy should equal 1. Is that okay? I'm just going to take the c out of the integral. Okay. Now what if part B, part 1 says find the probability that y is less than 0.3? Where would you be integrating between?
Oh, okay.
-1 to 0.3. Because where is your PDF defined from?
Oh, it starts at -1.
Also, I'm just going to sketch this curve for you. It's just a negative hyperbola, or concave down hyperbola. So like that. You guys notice something really annoying about this? Like you're integrating the exact same thing every single time.
It's good for marks.
And I'm kind of getting over it. Mhm. 71.825%. Okay, cool. What if I asked the probability that y is less than or equal to 0.3?
Okay.
Yeah.
It's the exact same thing. No, I'm just trying to be annoying. Does the all equals make a difference? Nope. What if I said y is greater than 0.1? This one you actually have to integrate. But don't worry about it. We're not going to do it because it's annoying. Oh, it's just another one of the exact same things. 0.1 to 1, right? For 1 minus y squared. And I'll just paste this in and I'll show you where it corresponds to. If it's just going to be greater than 0.1, then you put 0.1 on there, and it's going to be that. So we run into a bit of an annoyance, which is that we keep integrating the exact same thing over and over and over again, right? That's kind of annoying because yeah, surely there's a better way. There is a better way.
Ooh.
So the cumulative distribution function. Well, actually, let's
Yeah.
do a little bit of a cartoon for us.
Oh.
Musa is annoyed. I'm too lazy to keep integrating the PDF. PDF.
You don't have to integrate every time, you just go sub in the different numbers every time.
Yeah, but still, there must be a better way. And then we have another. This is Musa. He's sad.
This is probably the last time we'll ever hear that catchphrase.
And then we have another person here, and he's like smiling. Yes, friend. We can use the PDF, CDF. Great. Okay. So let's I have a friend, that's pretty cool. Let's figure out what they mean by using the CDF. So the cumulative distribution function, or CDF, is a very important function which can help save us a lot of time when finding probabilities, which is areas underneath curves. Consider all the examples we previously did. Every time we were asked to find the probabilities of certain intervals, we had to integrate the same PDF, and we just had to substitute different bounds, as Dion said. This can get very repetitive, and the CDF is defined in such a way such that it saves us time, and we'll only ever have to integrate once to find the probabilities. Okay? So let's say I had a generic random variable x, which we keep referring to, right? The one I gave by the survival function, right? And it's defined on the interval a to b. We've given the PDF. So x's CDF, the random variable x, it has a CDF denoted by this. Oh my, okay. Let's talk about what this means.
Where's the B coming from?
Yeah, I know. The T is funky. So just write this in. Just say if f of x is given by that, then CDF is given by this. Just so that we have it done. Sorry, I'm just going to quickly copy in this PDF. So we're trying to find something called the CDF. The CDF is the cumulative distribution function. Cumulative means, remember how we do it with Pareto charts? We say up to this point or anything less, like anything to the left of it. That's what your CDF tells you. Your CDF is saying, what's the probability? It's denoted by a capital F of X. What's the probability that X is less than or equal to a certain X value? So what does that mean here? It means like, let's say I'm only defined from A to some specific X. That there is the CDF. It's the probability my X is less than or equal to some certain X value. Okay? Like if I ask myself, what's the probability X is less than or equal to 10? I take capital F of 10. What's probably X is less than or equal to 0.3? I take capital F of 0.3. Because that automatically integrates you from the starting point up to 3, or up from the starting point up to 10. Okay? So that's why we denote it by this integral here. It's the integral from the starting point up to a certain X of this here is my PDF. So the PDF is denoted by lowercase f, and the CDF is denoted by capital F. Because when I integrate, usually I use a capital. Okay. Now, Dion, you're right. Why on earth do we use the T there? Okay. The reason why we use T is, as I've referred to here, it says, no, T is simply what we call a dummy variable. It's just a variable that we use as a placeholder in the integral that doesn't actually show up in the final result. Oftentimes we use T or S, but T is better because S looks like a 5, right? The reason why we do it is because it's not good notation to do something like this. Like technically, I'm never supposed to write, let's say I have the integral of from 0 to x of x squared dx. Imagine if I was going to integrate that. There's nothing really wrong. I can integrate that. The problem is, I'm now about to sub in x into x, which is kind of dodge. I'm never really supposed to sub the same variable into itself. So what we do instead is we say, I mean, first of all, let's actually sub it in, even though it's going to be dodge. If I sub it in, it's going to be x into x is just going to be x cubed. So 1/3 of x cubed minus 1/3 of 0 cubed. And it ends up being 1/3 of x cubed, right? But what I should have done instead is said, I'm going to take this here and I'm going to integrate from 0. Why is this so weird? From 0 to x, but instead of writing x squared dx, I'm just going to take it and write it in terms of another variable, some dummy variable t. When I integrate this, I get the integral of t with respect to t, the integral of t squared with respect to t is 1/3 of t cubed from 0 to x. And now I'm subbing x's into t's, which is fine because I'm subbing a variable into another variable. So then it becomes 1/3 of x cubed minus 1/3 of 0 cubed. And it still ends up being 1/3 of x cubed. So what you can see is like, it doesn't actually come up in the final answer. It's just a way for me to make the notation a bit more correct. Now, a few years ago, like not even a few years ago, I think last year actually, even the year before, my students didn't like using t's. They just did x's and said it's okay, I'm gonna sub x into x. I don't care. If you do that, like it's notationally wrong, but you're not going to lose a mark.
Yeah.
You're still going to get it right. It's just this is the fully correct way to do it. Okay.
Yeah, because I'm thinking like you don't even need to do it really. Like you know, if it's just going to equal -0, then
Oh, it might not necessarily always equal -0.
if it's like like e to the power of 0, I think it's fine.
Yeah. It's just the idea you don't want to put x's into x's. You'd rather put like an x into a t.
Yeah.
But if you put x into x, who cares? Maybe I'm just being a bit too annoying about it. Okay. So that there is your PDF. The integral from the starting point up to a certain value. So the CDF or f of x can be used over and over again to find probabilities of any interval asked. If we plot some generic, I already did this part.
Oh, so you can just plot the number in, and then it'll give you
The cumulative, yeah.
Okay.
So let's go back to the smartphone example and find the CDF for this. So the CDF, which we denote by capital F of x, is the integral from the starting point up to a generic x. And then it's an f of t. So I'm going to rewrite this, but I'm just going to put a t there instead of an x. And then dt. Okay, let's integrate. The integral of 1 on 50, which the t gets added to that, doesn't it? It's a constant. And then minus t squared over 5,000, but you're dividing by 2, so you can just put another 2 in the denominator. Okay. So now we just have an x and 0. Now, I don't mean to be annoying, but whenever you get given a PDF or PDF in a piecewise, your CDF should always be presented in a piecewise as well. So what would the piecewise function look like? Now, let me just first write it out, and then we can discuss why I've written it out the way I did. So just like how your piecewise is written in 3 separate components, as for your PDF, as it will be the same for your CDF. I'm getting so confused with these Prony rules. Okay, so here it's 0, here it's x1 50 minus x squared over 10,000. Here it's 1, and this is x is less than 0. There's x between 100 and 0. This is x is greater than 100. Okay, so remember what your PDF or remember what your CDF is trying to tell you. It's trying to tell you what's the probability that x is less than or equal to a particular x value. Remember, this is a smartphone battery example.
Yeah.
So if I want to find the probability x is less than or equal to -10, which part of my CDF am I going to be looking for? 1, 2, or 3? Which domain does this -10 sit in? The first one, right? What's the probability x is less than or equal to -10? What is the probability? 0, because it's not defined there at all. Okay, what if I have the probability x is less than or equal to 110? Which one does that sit into?
1, 3.
3,
Oh,
right? Because this 110 is more than 100. So I'm asking you, what's the probability that when the smartphone battery lasts 110 hours or less? Isn't it guaranteed to last less than 110 hours?
yeah.
Because it's only defined from 0 to 100. So that's why anything before the piecewise, it's always going to be 0. And anything after the piecewise will always be 1, because you're always saying like probability lasts less than or equal to 200 hours. You're guaranteed for it to last less than 200 hours.
Yeah.
The idea is that between 0 and 100, you have probabilities, and anything after, you're guaranteed for it to occur. That's why it's 0 and then 1. But then anything in between, let's say I want to find the probability x is less than or equal to 50, that's when I go to this one.
Yeah.
Okay. So that's how we write the final CDF.
Just depends on where the price.
Exactly. Very nice. Okay. So now using the CDF, now all you're gonna do, see how good this is? You've integrated once. That's it. Now you can just rinse and repeat using this CDF. So now if you want to find the probability that x is less than or equal to 50, isn't that literally the definition of a CDF? This is just going to be capital F of 50. So you go and you say, you just sub in 50 into the CDF. Okay. What about if I ask the probability that the battery lasts between 60 and 75 hours?
What, so you do. Like you sub it in and then minus it, like 75 minus 60.
Good job. Perfect.
Yeah.
So exactly. Now I'm going to redraw what this PDF looked like, and I'm going to show you what corresponds to what area. So it looked something like this. That was 100. X. This is some PDF. 60 is here. 75 is there. Now, if you had taken F of 75, that's the probability that X is less than or equal to 75, which means that's this full area. What if you had taken the probability? What if you had taken the CDF for 60? That's probability X is less than or equal to 60. And that would have been this whole area.
Wait, but with this now, because we've got the CDF, yeah, do we just type in 75 into that and then minus by 60? Is that all we have to do?
Exactly. So if you want to find the probability that X is between 75 and 60, even if you just look at the areas on the under the curve, how do you get that area? You get it by taking F of 75 minus F of 60. You can see you're left with what'd you get, Dylan?
9.75.
Thank you. Fair enough. So all you're going to do is integrate once, and now you have a something you can just rinse and repeat something into.
Yeah.
Okay, what if I said here the probability the battery lasts at least 40 hours?
42, 100. Or
Yeah,
what's the,
how could you use your CDF to do that?
yeah, just 100 minus 40. Oh, wait.
Yeah, yeah. You could do 100 minus 40, so f of 100 minus f of 40.
Or you could do 1 minus, 0 to 40. Yeah.
Yeah, but I think, watch this, like, if you're finding, like, let's say 40 is here, if you're trying to find this,
Just 1 minus 0 to 40.
perfect, but isn't 0 to 40 just f of 40?
Yeah.
Yeah, perfect. You can see how I'm writing it as well. This is just another way. Probably x is greater than or equal to 40 is equal to 1 minus probability that it's less than, and the probability that it's less than is the definition of a CDF. Interestingly, Dion, you said f of 100 minus f of 40. You're right as well, because you know what f of 100 ends up being? 1. So, because f of 100 means what's the probability that your smartphone lasts less than or equal to 100 hours? 100%,
Yeah.
right? Because that's where it's defined between. Yeah.
So technically, we're not even calculating it like, we're just calculating it one way, 1 minus.
Mhm.
Is that for every interval, I guess, when you're doing it like that?
Yeah, as long as the full area underneath the curve equals 1, then yeah. Okay, we don't have to do the last one. I just want you to write out what it would look like. Don't even bother subbing in. Probability x is greater than or equal to 30.
30, right? Would it just be 100 minus 30?
Yeah. And f of 100 again. Just pretty cool. So we're kind of going back to the example from before, and we're going to find their CDFs. So, okay, so we've got this one. The random variable x represents the time in minutes. We already read this. Can you just find the CDF of this one? And can you also write your f of x as a CDF as a piecewise, please?
That's a lot.
As a piecewise. So we have for x is less than 0, and we have for x is greater than or equal to 0. There's no like other element, is there?
What, do we just replace the 0 point, the second one, and just put the CDF in?
Yeah. And for the first one, it's still 0, isn't it?
Yeah.
There's probably that you're less than anything negative is going to be always 0.
To add something in.
Wait, that's fine.
Yeah?
Is it not? Wait, into B?
No,
Oh.
like I didn't actually integrate it, I just subbed in x and 0.
Oh, no.
Yeah, by the way, this one's. It's maybe one.
Hello?
Hello, how are you?
I'm well, just open that. Yeah.
Am I early?
No, you're good.
Yes.
Skip 5%. Yeah, too many decimals. Not bad, right? Is that okay? Yeah. What about x is greater than 10? Yeah, remember the 100 is from the previous example, right? This is just, you can just do 1 minus like complementary events. Yeah. Not bad, right? Perfect. That is PDFs and CDFs. So next time, I think this is a good place to end because the rest of it is very like it's a bit different. It's like still related to the PDF, but I gotta if I teach something, it's gonna take a while anyway.
Yeah,
But I think we've covered good ground today.
how much more is there? I mean,
So all we have to do now is probably like I think next class will be expected value or mean, mode, median,
Yeah.
and standard deviation. Those actually aren't that bad because everything kind of,
How to find them in context.
yeah, and just a bit of practice with it.
Exactly.
Yeah.
I mean, it's on top of it.
And then, because continuous random variables has two components. It has this continuous distribution stuff, and then it has the normal distribution.
Oh, yeah.
So within next class, we can even probably start normal distribution.
Yeah.
Yeah, and like that'll take like a lesson as well. And we're done. Yeah. Have interesting problems ready for us. Have interesting problems ready for us. It's my quest to find a girlfriend. Then what is this? The same smartphone battery one shows up a lot. All good.